This is the first in a series of videos on vector calculus. We will go over how to set up the coordinate system, how to state and plot vectors, and state and plot vector fields. Let's get started. Since we're doing a lot of work with the vector calculus package, this is one of the few times it's worth loading the entire package with vector calculus. As you can see, there is a bunch of procedures available. We will not be looking at all these procedures. However, we will be taking advantage of the operators that vector calculus provides. One could load the student vector calculus package. I choose not to because I like to explicitly write out the properties of the vector space. Now that you've loaded the vector calculus package, you need to set the coordinates. Set coordinates with an S. Name the system you'll be using, in this case Cartesian, and then give it the list of coordinate names, X, Y, Z. Now everything will be assumed to be in the Cartesian coordinates with those names for the coordinates. We also can use the cylindrical coordinate system. I prefer to use the variables of rho for the radial component, phi for the angular, and z for the z-axis. Finally, most popular coordinate systems that physical scientists and engineers tend to use is the spherical coordinate system. In this case, the names I'm going to use is r for the radial component, theta for the angle that comes off the z-axis, and phi for the angle on the xy plane. This may be different than you see in a math course where theta and phi are switched. However, if you write it in Maple this way, this is how Maple will interpret the spherical coordinates relative to the x, y, z coordinates. Again, phi along the xy plane and theta the angle off the z-axis. So again, load the vector calculus package, then set your coordinates to the system you're choosing and give the coordinate names. Now we're ready to create some vectors and vector fields. The vectors in the vector calculus package are different than the traditional vectors in Maple. Let's create one with a vector sign. V, Command Shift, double quote, dash, greater than sign, or you can use one of the accent palette vectors. Go to the right, underscore, underscore 1, go to the right, colon equals, A, B, C, just like you do in any other vector. Notice the output. There are the components A, B, and C, but now the unit vectors are labeled E sub x, E sub y, and E sub z. The alternative way is to call the vector procedure, which has been loaded from the vector calculus package, so it's different, passing it the components. Finally, you can write out a vector with a specific coordinate system, again giving it the coordinate names of a vector where here are the components. Now it is in the system of the cylindrical. There are the unit vectors. But again, we haven't changed the default system, which is still Cartesian. If you wish to plot a vector, it is usually easiest to plot it in Cartesian coordinates. Let's do a 2D plot. This sets a 2D coordinate system of just x and y. And we'll create two vectors, v1 and v2. And again, there are only two dimensions, so there are only two components. When plotting an arrow, while there is a plot vector procedure in the vector calculus package, I still prefer to use the arrows procedure out of plots. In this particular one, I'll also give it a legend using the typesetting technique so it shows a V1 or a V2. And I will therefore plot the two plots here using the plots display procedure and scale it to its constraint. The default of plotting any vector, unless you give it a location, a route where to plot, it will plot from the origin. And if we wish to plot in 3D, we need to change our coordinates to a three-dimensional system, define our vectors, and again, plot them such that they have some different colors and we'll put this in the plots display, and you can see there's the R1 and the R2. You cannot put a legend in for a 3D plot. Now we move to the next important entity in the vector calculus package. These are vector fields. A vector field is a field of vectors. In the worksheet, they are distinguished in the output from the vector by the format of the basis unit vectors. For example, big V is defined as a vector field, and then you give it the vector field vector as in A, B, C. As you can see, the output is similar to a vector, but now the fact that the field can change at different positions is given by the unit vector, which can move around, and they put a little bar over the top. Again, a vector is a vector at one location. A vector field is something that can be spatially differentiated. Like vectors, we plot vector fields using a procedure from the plots package, field plot. Let's do one in the 2D Cartesian coordinates. Here's a vector field, and using the fields plot procedure, we type plots : field plot, open parentheses, our vector field, comma, and then we have to give it a range from -10 to 10, and y goes from -10 to 10. Since field plot tends to put too many arrows in, you can change the grid size by putting in something smaller. This one is much more readable. Here's an example in 3D Cartesian coordinate system. Frequently, one needs to change the basis of a vector. The map to basis procedure performs this action. Assigning to a new variable, we map to that basis of our vector, which is going to be in spherical coordinates, using these coordinate names. Notice the results do use the components of the vector, but write them out such they appropriately work in the coordinates that we've changed to. Here is another example where we have converted our A, B, and C in Cartesian to something in cylindrical coordinates. Now let's talk about plotting a non-Cartesian coordinates vector. For example, in this vector, we have one that is in spherical coordinates, even though our default coordinate system is Cartesian. If we display our arrow of this spherical coordinate system, we get a result which doesn't make sense. For example, we're expecting this object to be of radius 1, but is purely on the xy plane because theta is pi over 2. And yet our plot here doesn't show the arrow pointing on the xy plane. That's because arrow has decided that this is the x component, that's the y component, and this is the z component. One way to avoid this confusion is to map our spherically based vector into Cartesian coordinates and then plot it. Notice now our arrow truly is on the xy plane. So we have gone over how to set up coordinate systems, how to label and plot vectors and vector fields. The next video will go over operations onto vectors and vector fields, such as divergence and curl.